Hello everyone, I'm Tianfang Lin from the Chair for Computer Graphics and Visualization, TU Dresden. I'm very happy to present our recent work, PointShop VR, Immersive Authoring of Large Point Clouds in Virtual Reality. This work is together with Professor Matthew McGinnity and Professor Stephen Gumhold. Point clouds are widely used in applications such as environmental design and creation of metaverse environments. However, for massive point clouds produced by LiDAR photogrammetry and other state-of-the-art 3D scanners, there is a lack of efficient interaction tools, which makes authoring point clouds for creating immersive environments very challenging. Several issues are existing in authoring point clouds. First, conventional editing tools focus on tasks like segmentation, registration, and mesh reconstruction. Second, 2D screen-based interfaces are often hindered by heavy occlusion, as shown in the left figure. Further, VR could help users select points with depth perception, but it requires high frame rates of 90 Hz or higher. For large point clouds over 100 millions of points, providing instant visual feedback is very difficult. Based on these insights, a central challenge arises. If we want to deal with large-scale point clouds in VR, naive implementations that repeatedly traverse the entire dataset cannot provide fluid real-time interactions. Therefore, we ask, first, how can point cloud interactions be efficiently enabled in VR? Second, how is the authoring efficiency compared to traditional desktop-based workflows? To address these research questions, we revisited the prior work in three aspects. First, in 2D 3D editing authoring tools. In 2002, PointShop 3D presented a system for interactive shape and appearance editing of 3D point sampled geometry. After that, a series of 2D and 3D desktop-based editing tools like RealityCap and Pointly AI emerged. But the steep learning curve and heavy occlusion in the point clouds often make point cloud editing a time-consuming and labor-intensive process. Second, point cloud interaction in VR and AR. Carlos presented LiDAR Viewer was one of the first immersive visualization and analysis systems for large-scale LiDAR point clouds, but it does not support manipulation of point cloud geometry. In recent years, PointShop AR and Gaussian Shop VR offer addition, deletion, modification, and animation of the immersive point clouds. However, they are limited to relative small size of data. With the increasing availability of GPU computing capabilities, continuous level detail rendering was introduced as an efficient approach for large-scale point cloud rendering in VR. Lin further improved scalability by introducing a hybrid CPU-GPU data structure, enabling immersive labeling of large point clouds at 90 Hz. However, this approach primarily focuses on visualization and coloring in VR without enabling true geometrical editing. Therefore, immersive geometric authoring of large point clouds remains unexplored. To enable the geometric authoring for large point clouds in VR, we derive two goals of our system design. First, we aim at designing an accelerated data flow architecture that balances rendering and interaction in VR. Second, the system should support both point-level and object-level operations as the minimal interaction sites for immersive authoring. This includes creation, deletion, query, and geometric modification. Next, we introduce the key components of PointShop VR system. First, to enable real-time interaction with massive points, we adopt a trunk-based selection and modification strategy. Instead of traversing the entire point cloud, operations are restricted to chunks of interest, significantly reduce computation and ensuring stable frame rates in VR. Second, to integrate the basic authoring functions, as shown in the figure, we designed our mixed CPU-GPU data flow. On the CPU side, The points are partitioned into chunks, and the chunked points are uploaded to GPU buffers. On the GPU side, we deployed computer shaders to perform per-point operations in parallel, including selection, labeling, physics-aware pushing, and rendering. We also introduced a clipboard buffer for previewing candidate point clouds, and a clipboard array to support point cloud duplication and integration of new scans from local drive and RGBD cameras. Based on the mixed CPU-GPU data flow, PointShop VR offers basic authoring functions such as moving, adding, copy-paste, and physics-aware pushing. We illustrate the workflow as shown in this figure. An original scene of live is shown in the figure A. The user copy a table and paste it to another place. Import a sofa from local drive and position it using grabbing-based manipulation. Lift the leaf of the plant by using physics-aware tool. Finally, we could see in figure D, the final meeting room is composed by rearranging multiple objects with intermediate visual feedback in the immersive point cloud. Guided by research question 1, we evaluated the performance of our system across multiple large-scale datasets, ranging from 82 to 139 million points. The average frame rates are close to 90 Hz during continuous rendering. We also observe frame drops during copying and adding operation, primarily due to the data transition between CPU and GPU. In the worst case, these events manifested as a single frame hinge at the operations on trigger, after which the system immediately resumed to 90 Hz. To address our second research question, we conducted a user study comparing PointShop VR with Blender. We recruited 18 participants to complete two authoring tasks of outdoor scene and indoor scene. As shown in the figure, we presented the workload results based on the NASA Task Load Index questionnaire. Compared to Blender, PointShop VR shows significantly lower scores in tempo demand, perceived performance, effort, and frustrations. Mental demand also trends lower, although with weaker statistical significance. Additionally, PointShop VR significantly reduced task completion time compared to Blender in both scenarios. From the study, three key differences emerged. PointShop VR provides spatially aligned selection, instant visual feedback, and intuitive candidate preview. Through these advantages, PointShop VR significantly reduced task completion time compared to Blender in both scenarios. Our method has several limitations. First, object placement relies on users' manual judgment, which may limit placement precise in complex scenes. Second, lighting is not dynamically updated after object duplication or repositioning, which may reduce visual consistency. In conclusion, we presented PointShop VR, a system that demonstrates the feasibility and efficiency of immersive authoring for large point clouds over 100 million points. By extending from immersive labeling work, our system enables not only selection and annotation, but also metric editing operations such as moving, adding, copy-paste, and physics-aware pushing. A prototype implementation and a user study confirmed that immersive VR interactions can greatly improve the efficiency of point cloud authoring compared to conventional tools. In future work, we see several promising directions. First, implementing parallel data upload and rendering using multi-threading via linked OpenGL context to make the system more stable. Second, supporting collaborative authoring. Third, integrating AI assistant authoring and explore mixed reality platform. Thank you very much for your attention. For more technical details and the evaluation results, please refer to our paper.